Resampling, resizing the pixels. So previously we've looked at just a simple rotation. We haven't changed the pixel size at all. Same pixel size, and that seems good. But there are times when we will want to resample to a different resolution, a different pixel size. Generally speaking, the rule of thumb is never ever resample to a higher resolution. That's the rule of thumb. You can, if you have extra information. If you have other information that says, I know what might be happening at a higher resolution within each cell, each pixel, such as some covariate of a higher resolution, or if you have a so-called mixing model where you say that values in a pixel are due to mixing from neighbors, and I believe that here we have a high center for a particular signal strength, and that's bleeding into this one. That's why this has got some of this value into there, and I can remove that and put it into there and increase my resolution on this, so that this data actually over here becomes even lighter, and over here it becomes darker. Something like that. This is a model that you may have access to. It might not work. So generally speaking, you do not resample down to a higher resolution. You can resample to a lower resolution. That's not entirely problem-free either, but you can do it. That's less of a problem. You're not introducing new information. You are taking what you know about an area and then generalizing it up. Now that might not always be correct either. That's a more advanced consideration, but let's just say for now that resampling to a lower resolution is, generally speaking, that's the safer option and almost always applicable. So we can go from lower to higher resolution. We take the information that's in those pixels behind here and just generalize to another larger pixel. And here we haven't even considered a rotation, but we can also do this together with a rotation as well. And this process will happen at once. Now we don't need to go via first a rotation, then a rescaling. We can do it all at once in one process. And why, just as an example as to why not resample to a higher resolution. Hopefully you've seen this before. Let's look at elevation data and calculating slope, for example. So here we have data with a particular resolution. Here's the ground sampling distance, the support for this measurement. We had some method for gathering information on elevation, and it requires a particular area on the ground in order to gather the information needed to make that measurement. It's the support. And that's equivalent. We've chosen, when making this survey to begin with, we've chosen a cell size that best represents that support on the ground for making the measurement, and we have our elevation model here. And then we've rather naively decided that we're going to increase the resolution, create smaller pixels, and just halve the size. So we have 4 pixels per pixel now. Only 2 here because we're looking from the side, obviously. And so we've increased the resolution, but we haven't introduced any more data. Well, okay, that's so long as we're looking at the elevation, this isn't perhaps terribly much of a problem. It still looks the same when we're looking at the elevation. But when we then move on to measuring slope, well, this is the support, the correct measurement here, and the slope at that measurement look like this. But now when we increase the resolution artificially without taking into consideration our support, well, now our slope becomes much steeper. Steeper than is perhaps correct. We don't know what the slope should be at this resolution with this much smaller support because we haven't measured that support. And so this is incorrect. And you will be able to see this in elevation data and slope and other derivatives of elevation data. If you see something that looks kind of like terracing, so you get step down lines going around in your data that probably aren't actually there. Obviously there are situations where you will see terraces. That's why we're using the word terrace, because it's a phenomenon that we can recognize from reality. But if you're don't expect to see terracing somewhere and you're seeing it in the slope data, for example, or in aspect as well, or curvature, then you have probably made this mistake, or somebody has made this mistake. They've resampled to a higher resolution when they shouldn't have. If you need this resolution, I'm afraid the only possible solution here, well, there are a couple of solutions. The best solution is to do a new survey with that support in mind. Increase the actual resolution of the data you're gathering in. Alternatively, you can try doing things like resampling using splines, or you can use perhaps doing bilinear or cubic, and hope that these are linear trends, so that you can add some information here and say it's probably going down quite rapidly there. That's a possibility. It's still not going to be entirely correct because you are making an assumption. Obviously, we have to make assumptions, and maybe that assumption is correct for most of the image, maybe it's not. So this is definitely an issue to be aware of. And this will affect, obviously, not just elevation data, it affects other types of data as well, but this is quite a good illustration, easy to understand. So where does this come from? And I've been talking about support and the information that's available to us. Well, we've mentioned this before in previous courses, something called the Nyquist frequency, where we have the minimum size of an object that our survey equipment can actually survey, capture changes in an image, in the terrain, in whatever it is, a sound signal, a light signal. This applies to waveforms, applies to spatial data, applies to pretty much all data, that we have to sample at the highest frequency, or a frequency high enough so that we can actually see the object. So here we are sampling with a frequency where we just about managed to capture the information here. We've got the peaks and the troughs captured. We've managed to basically get the relevant information, and with a couple of other assumptions that this is a sine wave, we can recreate this waveform accurately. If we then have a signal that's coming at a lower frequency, so our sampling frequency is higher than the natural frequency of the thing we're interested in, the size of the object we're interested in, then again we can capture enough information to adequately recreate this signal. We're getting all the peaks and troughs if we make a couple of assumptions that there's a sine wave behind this. If, however, we have a waveform that is of a higher frequency than our sampling rate, we end up missing important information. And when we try to recreate this signal, we end up with something that looks like a lower frequency signal. So we've missed it. There's information there. There are peaks and troughs that we have missed because we haven't been able to sample with a high enough frequency in order to adequately model that signal. So this is why we don't have the information in our original data in order to adequately, in all cases, sample to a higher spatial resolution. So, to summarize the resampling problem, resample basically in your workflow as late as possible. Try and do as much as you possibly can in the original data, just because it will make life simpler, and you'll be working with the true data. If you can't maintain the pixel size, let's say you're having to work with other data sets and you really need to transform your data, probably the best thing to do is to downsample to a lower resolution. You're going to encounter fewer problems that way. Upsampling, if you have extra information. If you've got something that correlates with your data with a higher resolution, you can say these two generally follow each other, this signal and that signal. This other signal I have is a higher resolution, and I can use that extra information to help resample my other data. Then that's possible. Depending on the how well it co-varies. If they correlate completely as 100%, what's the point then? You don't need the other data. You've got all the information you need in your covariate. But if they don't covariate to 100%, then you're getting extra information. But then obviously, by that definition, maybe, there are places and cases where it's not actually going to work. So it's a little problematic. The other way you can get around this problem is if you're just not going to do any analysis. If it's purely for visualization, or if you are doing the analysis by hand without looking at the spectral values or anything like that, then yeah, maybe you can do that. But don't be fooled into thinking you've got a higher, even if you're doing delineating objects in your image, digitizing them, you don't have the resolution of your resampled image. You still have the resolution of the lower resolution image in your resultant data, but you won't get any other problems whilst doing your digitizing. You won't have introduced any artifacts that are going to disturb you. So that should be okay in that sense.